Okay, so what I'm going to be presenting is a traffic control problem, and just from the get-go, I want to tell you that I'm trying to do traffic control for physical things, so not network traffic, so keep that in mind. So this is some work with my advisor, Sayan Mitra, and Karthik as well in our group. So let's move on. So as a general outline, so I'm going to introduce this problem, and again, physical things, not network traffic. I'm going to introduce the problem, and then using pictures instead of math as much as possible, I'm going to give you an idea of the system model that we used and the rough analysis and try to convince you of that this works. And then also I have a simulation at the very end showing you that it works. So let's dig in. So the motivation of this is that in traffic control, traditional traffic control, such as air traffic control, there's some centralized coordinator. In this case, the traffic tower is telling some planes what they should be doing in some regions. Okay, so inside of this tower, we have these guys looking around doing this. They're telling the planes where to go. And so if we look at it from a bigger picture, in some sense, this is a map of the US, and it's been divided into regions or partitions. And within these regions, the traffic controllers are telling the planes what they should be doing. So that we avoid collisions and that things get routed where they're supposed to be going. So now, of course, this is kind of a modeling abstraction. The planes could deviate from what they've been told to do, but we're going to, in the model we're working with, we're assuming that the physical entities will be routing, will not be deviating from what we're telling them to do. So this is high level. So we have another picture of some software from just showing some more divisions of space into these regions that I mentioned. And I wanted to mention another possible application aside from, say, air traffic control or routing on roads would be routing in factories. So we have a conveyor belt moving some packages around. So in a lot of factories, so one key property we care about is avoidance of collisions or safety. And in factories, maybe you actually utilize collisions to keep things moving along a conveyor. But so we're not really considering applications like that. But in general, this is where we're headed. And so the model we're going to be working with, so this conveyor has the ability to move in several directions. So it can move this way, and also it can move this way. So this will become important if you want to think about the model we're working with as describing some sort of a multi-directional conveyor system. And you'll see that in a second. So what is, I think I've introduced the problem okay. So we've got some physical entities, and what we're trying to do with them, we have maybe some sources and destinations. We're trying to get these things safely from sources to destinations. So how do we do this? So we have some traffic control protocol. In the air traffic example, there's a protocol that the operators are following to ensure that this happens, that we're moving these entities along the way, and that we're avoiding collisions. And when they deviate from this behavior, things can go wrong, and they have in the past. But at any rate, so these are rules for routing some entities through some underlying graph. And the underlying graph could be regions and some partitioned space, such as airspace, or it could be, we could look at it as waypoints along a road. So we have some underlying graph. And the entities are aircraft, cars, packages, whatever. And as I've said, we want to be maintaining safety. And also, we have another property called progress, which is that things actually get where they're going. Because without a property to specify progress, it's very trivial to satisfy safety. Nothing moves. So everything just stays where it's at, right? So these are the properties that we have. So that's what we're going to be analyzing through the rest of the talk. And what I'm going to do is I'm going to present a distributed algorithm that's self-stabilizing. And it's going to find a route in the underlying model we're working with, and then it's going to move all of these entities to the destination. And I have, there's also another question. Traditional modeling of networks, or in any sort of system where we're trying to move things around, we care about throughput. And so the way we've defined throughput is, or average throughput is time or the number of entities arriving at a destination divided by the time it took to get there. So to motivate a little bit more the modeling abstraction we're going to work with, I want you to imagine the last time you were in heavy traffic. I'm thinking like driving your car. And just imagine you're in this situation. So maybe for some of you it looks something like this. This is from Delhi, and it looks like everything is completely stopped. So the point I'm trying to make here is that what's the relative velocity of everything in this region? It's 0, right? So nothing, everybody's stopped and nobody's moving together, or they're all moving together. So likewise, we have a picture from, I think this is Beijing. So if we look in this region, these cars are moving in somehow a same kind of relative velocity. If we actually look at the second derivative, they're also slowing down simultaneously so that they don't collide with the vehicles ahead of them. So there's a coupling between the motions and between the velocities and the accelerations of all of these entities. And then just for fun, maybe this picture makes more sense to some people. Anyway, I'm from Houston, so this is from Houston, a little bit older, but at any rate, we've had traffic problems for a long time. So how are we going to model such systems so that we can actually prove properties like safety and progress? So in general, this would be very difficult, right? So these are highly nonlinear systems. You can get into situations where traffic all of a sudden stops, phase transitions, things like this. And one point I kind of sort of alluded to earlier is that flow networks can't really capture the notion of safety that we're trying to get here. So at least as far as I know, there's no way to pull in, or no clear way to pull in our notion of safety, of no collisions occurring. So it's more so concerned for throughput. So we're going to work in a discrete transition system. And I have a synchronous assumption that all of these processes are working in a synchronous time model, and they have shared variables. And so what we'll demonstrate again is invariance of safety. So all states that are reachable remain safe, and convergence to states that actually make progress, and also stability of those states. So once you're there, upon certain actions stopping occurring, it'll continue. So this is, to get a little bit more concrete, this is what the modeling abstraction we're working with. So this is the 2D real plane, and I have a grid of n by n cells lined up with indices from 0, 0 up to n. And the physical entities are represented by these square boxes here. So there's some safety spacing d around the so d by 2 from the point. So we could represent it in a variety of ways. We decided to pick the center point. So we want to the safety property we're going to try to maintain is preventing any points from coming d distance within one another. So our formulation, as I said, so we've partitioned the real plane into unit length squares. And also, so neighboring cells transfer entities between one another. All entities on a cell move with some fixed velocity. And why does this make sense? Well, the coupling that I mentioned a little bit ago, it's reasonable because everything's moving with the same relative velocity. And so there's an additional challenge we introduced, which is that we have permanent failures of some of the cells, as we're calling them. So these unit length partitions are called cells. So some of these will fail, and I'll get more into that in a second. So I'm going to try to get through as much of the system model and analysis as possible. So the algorithm runs in 2 phases. The underlying phase finds a route. And this is the part that's self-stabilizing. So we always find a route if one exists. And then also there's signaling amongst the neighboring cells so that they ensure progress and that they do so safely. So, okay, so from the previous picture, so we have some flow of these entities moving from the source to some sink. So we're just talking about single source, single sink. It's easy to generalize to multiple sources. Multiple sinks become slightly trickier if you have specified destinations for some packets as opposed to others, but it pretty much generalizes straight away. So they're following some path to get here. There could be another path, but let's think about this one. So if we look at the distance from the sink along this path, so this cell is at distance 1 away, 2, 3. And we're going to use this notion based on the way that we've divided the region to come up with the route. So first off, I want to give a little bit of a definition to what the neighbors of a cell are. So it's It's just the ones right around it, like this. We could define it in this way, with Manhattan distance, however we want to do it. So these are the neighbors. So the basic routing protocol, you look at what all your neighbors' distance is to the sink, and you take the min of that, breaking ties with IDs if you need to. So the sink advertises that it's 0 distance away from itself. All of the neighbors of sink learn that, so they become distance 1, and they want to go towards the sink. Likewise, all of their neighbors are distance 2, so on and so forth, 3 and 4. So this part of the algorithm has found a path to the sink from any other cell in the network. So I want to go back to the failure model briefly. So once a cell fails, it's always failed. And so there's 2 different types of things that we're thinking about as far as failures could go. It could be a physical failure of the cell, where the actuators have failed in such a way that the cell no longer has the ability to move, in which case that cell could tell its neighbors that it's failed. The distributed computing way of looking at it would be that the system, the process controlling a cell, has actually crashed, and that the state machine has stopped taking steps. So that's the alternative way. And this could be detected using timeouts, things like that. So, and why is this neat? So this allows us to get some kind of a quantitative measure on failures of both software and physical entities. So this work is towards a kind of general theory for failures in cyber-physical systems. That's where we're going with this kind of simple example. Okay, so let's fail something so that we see what happens. So a failure, what happens is that now if a node fails, we learn that its distance is actually infinite to get to the sink. So these nodes learn that. So what happens to the path? So clearly the source can't go through this anymore. So it reroutes and picks the nearest neighbor or the lowest distance neighbor that is non-crash still. So another path is found like this. The entities on this would still continue to flow. These entities are stuck here forever. So the actuators, or if the process has crashed, it's done. You can't do anything else. So likewise, we can have failures that cause partitioning. So what we're going to show in the proofs, we'll kind of outline, any entities, any of the packets in a region that is still connected to the sink eventually get there. So that's what we want to do, and we can't talk about any of these things. And the other thing, if you know this counting to infinity problem, these distances are going to count off to infinity. And these pointers of what they believe their next path is, they're going to keep changing. So what we're going to maintain, though, is invariance of safety in spite of this occurring. So safety is still satisfied despite this part of the system being wrong, being really wrong. And the rest of the system still maintains safety, and it also makes progress. So as I said, these nodes don't have a path to the sink, so they don't have progress. These are still target connected, so we'll get progress. So how does the signaling work so that we maintain safety? So the general idea is that each cell looks in this region of D, which is the same length that we're trying to maintain amongst points, and looks to see if there's any entities there. If there aren't, whoever's pointing at it gets the ability to move in this direction. So that's what happens. So the packets all move by V and around. And some packets may transition. And what we've assumed is that if an edge crosses the line, the entire thing goes. So that's the assumption we're working with there. So now there is, in fact, a packet here. So this cell no longer has the ability to move in this direction. So that's what it learns. So there's somewhat of a problem with this, right? So this is fine for safety, but how do we then still get that we get progress? So how do we get progress out of this? So if eventually ij moves, then eventually its neighbors will have the ability to move. So that's what we'll show. So the question that arises from that then is, where is ij pointing? So we need to look at its neighbors. So it could be the case, if it were failed, that it could be pointing this way. However, let's say that it's the correct one. And in fact, it will be the correct one so long as it's still connected to the sink, because the routing algorithm is self-stabilizing. So it's still found the path to the sink. So the caveat is this occurs eventually after the routing algorithm is finished running. So after the route's been found, and only if it's still connected to the sink. If not, you can't say anything. It's not possible. Right? So then the final point of the algorithm is then which neighbor of ij gets the ability to move in a situation like this. So the algorithm is working in the same way. All of these safety regions are being checked. So to maintain safety, we need mutual exclusion. Clearly, we can't have both of these moving at the same time because it could be the case that they'll both transfer packets, these packets here, in which case our safety property would be violated because they've collided. Likewise, though, we can get deadlock situations. So we also need fairness. So if we had a situation where there was a stream of packets coming in, we need to fairly switch between these two to allow this to continue. And eventually make progress. So just I'm going to give you a very high-level view of how the proofs work out. So the idea is we have a state space, and we have a set of safe states and some initial conditions. And let's say we're starting at point X in this, and then we have the rest of the state space. So what we want to do is we want to look at what states are reachable upon running this algorithm and transitioning around. So we get to some reachable set of states. And we also defined an invariant which over-approximates this reachable set, because the reachable set could be very difficult to describe. So if you wanted to try to automatically verify this, you would need an easier-to-describe invariant property that you're maintaining to be able to say this about the whole reachable state. So likewise, however, because we have failures, we actually can get outside of this set. We have a larger reachable set. So if upon a failure, we get outside of this to some xf. And finally, to maintain progress of the packets, we would need to show convergence of xf to some xs, which would be a stable route. So this is the first phase of the algorithm. And then eventually, it still remains within this safe invariant. And finally, it makes progress towards the target. So I can run my little simulation. I think maybe I have to... I tried it earlier, so I know it works. The computer would hurry up. Okay. So right. So maybe I'll just start it over. Right. So we have a simulation of this. So this is the first phase of the algorithm. The route's being found with these green lines. These entities are moving through the system. There was a failure of a node of a cell here. So a new route was found towards the sink. And the entities move around. Some more failures occurred. The routes were updated. And the progress continues, and eventually these will make it to the sink. So we can do more and more complicated simulations of this. Every cell can be a source, so on and so forth. So at any rate, so this hopefully convinces you what I've said makes reasonable sense. And almost out of time. So we've also done a little bit of a throughput analysis. So in the simulation that was just shown, there's an issue with throughput as a function of turns due to the way that we've defined the safe signaling. And this just indicates that as the number of turns along a path increases, the throughput decreases. That's super interesting. So the conclusions and generalizations, and hopefully a few questions you'll have. So we presented a self-stabilizing distributed algorithm which solves a particular traffic control problem, which we tried to motivate as being looking at partitions of airspace or roadways, things like this, or factories. And then I didn't give you formal proofs of invariance. We have formal proofs of invariance. I thought it would be more interesting to have pictures. And we also have formal proofs to ensure progress. This type of a system generalizes easily to a 3D space instead of 2D using cubes and the same kind of signaling rules. Future directions, instead of using squares or cubes, may be arbitrary partitions. They may need to be convex. We've thought about it some. It gets a little hairier. And then I think another interesting direction is how do you maximize throughput while maintaining safety. So this would somehow try to bridge the gap between flow networks and what I've described here, which we can talk about safety with. So thank you, and if there are any questions? Yep. So I'm not an expert in air traffic control, so I'll say that. I mean, I don't really know. So I know that there is a protocol that's followed as far as the traffic controllers telling the pilots what they should do. They have specific language they're supposed to use as well. And if they deviate from this language, I mean, if you say OK instead of Roger, there was a, I forget the name of it, but it was about in the 70s or 80s, there was an accident where two planes collided on the ground because one was trying to take off and the other one had not cleared the runway. And it was caused to some extent due to improper use of language and as well as weather effects. But as far as an actual algorithm, I think just majority of it is pretty manual. So yeah, but future, that would, yeah, I think that's the direction things would be heading, along with like the automated highway system as well for cars. So, yep. Actually, what?
You said in your future work you will just consider the convex.
Well, right. That's yeah, it's a proposition.
Is it because the limitation of your algorithm or just
I think it's a limitation of the way that we're doing the signaling and the geometry. Because it's unclear how you would define this region if it were not convex, I think. So somehow you have to come up with a safe region that is being used to signal amongst things. So I think convex makes sense for that. But all right. Anything else? Yep.
So you're making assumptions from the synchronous timing model.
Right.
But does it apply for both the cells and the entities? So everything are.
Yes. Yeah. Yeah. It does. Yeah. So. Yeah, it's a strange abstraction to some extent. So the way we've represented the entities in the formal model, they're in a shared variable that's a set. So it's updated synchronously, yeah. But you could look at that as being the end of a round, right? So they moved for some period delta, and at the end of that round is when, yeah, that's where they were at the end of that. Yep.
Seems like you had a fixed set of pieces that had to get routed, and eventually they all got routed, but in a lot of systems you'd have like continuous arrivals. I mean, you know, new parts coming in, or you know, if you sent all these planes to Chicago at once, you'd like to.
Right, that's an easy problem to solve, I would think. Yeah, so.
It needs like some kind of admission control or something, and then you'd also like to have some kind of performance of how much delay there was.
Of adding new.
Well, besides having a finite set eventually reaching the destination, I would think you'd want to have some other measures of delay, or you could have back pressure or something for emission control. So you can't take off from Los Angeles if there's planes through the air all the way
Right.
across.
So to some extent, we do capture that. So if we look at, so this green cell in the simulation is a source, so it's adding entities. And it only does so safely. So that's the caveat. It also has to be fair. So we do add them. The way the proofs are structured, though, they talk about things once they're in the system, yeah. But yeah, it would be neat to try to capture that, I guess, more so in the model. That's true.
Or if the sources are far away, but then there's excessive congestion near the destination.
What is the effect on throughput and?
Well, you want your planes to take off if they're going to have to circle around the destination for 2 hours.
Right. Right. So yeah, so in general, if there are more, so we can have more sinks. So the only thing we can talk about throughput with is through simulation with this model. But we can have more sources as well. So I mean, we can have sources here, and in what happens is from one source, their throughput will decrease as you increase the number of sources. So that will occur because the sink will be serving the other source for some time. So.
Through back pressure, so you wouldn't be able to get in because all the cells would be filled.
Right, yeah. So they're just waiting, yeah, yeah. All right, thanks. Anything else? Okay, thank you.